So let's move on to the topics that are going to be on the final exam. I think actually one of the other things that, and you all are doing this, is coming to lecture, right? Is taking notes and, listening in and paying attention during lectures. Probably the number one thing you can do is that to start with. Okay, fundamentals of engineering exam statics topic. Now the FE is usually something that's taken your last semester of your senior year, and various majors have different versions of this exam. Lots of different majors take the FE. It's part of the process in becoming a licensed professional engineer, which gives you the ability to stamp drawings and stamp designs and say, yes, go out and build it. I'm approving this to go out and get built or manufactured or whatever the case may be. So the FE exam has statics on there, and our statics topics include resultants of force systems. That was a long time ago. We've covered that. Concurrent force systems, that's like trusses and just particle equilibrium. Equilibrium of rigid bodies, we've done that. Frames and trusses, we've done that. Centroids of areas, we've done that. Area moments of inertia, we have not done that. And then friction, we have done that as well. Well, area moments of inertia, we're going to start that today and spend the rest of the semester talking about the area moments of inertia. Okay, so area moments of inertia, it's actually, you're going to see it called a few different things. The second moment of area is actually the mathematical meaning. And then also you're going to hear me say a lot of times to shorten it up and just call it a moment of inertia, but it really is about the area moments of inertia. This is not the same as like inertia in terms of like something spinning and the mass moment of inertia. This is the area moment of inertia. And so we're going to start our learning objectives here by describing the physical meaning of the moments and also something called the product of inertia. So we'll talk about what is this area moment of inertia. We're going to start with differential elements that allow us to solve for the moments and products of inertia, which I stands for the moment, and then X, it's with respect to the X-axis, the Y-axis, and then the product of inertia is IXY. Implement then the correct integral to solve for those. And so drawing that differential element is going to be super key to allow us to solve for those. We'll also talk today about what conditions make IXY equal to 0. The product of inertia does not really have a physical meaning. It has more of a mathematical meaning, and we'll talk about that. And then use integration to find the moments and products of inertia for a rectangle. So we'll talk about that today and then continue talking about that really the rest of the semester. So let's start by talking about the physical meaning of the second moment of area. And I have a few pictures here for us to discuss this. We have in the past talked about, like, if we have a simply supported beam with a concentrated force applied to this, well, we're going to end up with tension on the bottom and we're going to end up with compression on the top. Well, there's something else we haven't really talked about, and it's called the neutral axis. This is actually where we have zero stress. So there's no tension or compression at that location. Well, there's a linear transition from this location of maximum compression up here. So that'd be a max C down to here where we have a max T. Well, that linear transition is such that at the neutral axis, we go through that 0 point right there. Well, if we look at a board here, so let's take a 2x10 or whatever this is, and if we walked across this board, if we oriented it like this, where away from the neutral axis, which is going to always be at the centroid of area right there, so we can see we have quite a bit of area that's away from that neutral axis. Now, if we orient it like this, we don't really, our neutral axis is still at the centroid right here. We really don't have very much area away from that neutral axis. And so we're going to sag down a lot more. We're going to see a lot of this sag in here. and we get a bigger deflection right there. Same board, same material, same area. Just like if I take a yardstick here, and if I orient it like this, I can bend it pretty easily because it has a smaller moment of inertia relative to bending in this direction. If I try to bend it like this, though, there is no way I'm going to get it to even budge whatsoever. Same idea of these pictures of this person walking across the board. So orienting the area further from the center gives us a higher bending stiffness. So that's really our second moment of area, is the geometric part of that bending stiffness. We don't need to know this equation, but the deflection in this case, if we have a point load, it's like 5 times P L to the fourth over 185 E times I. Well, this P would be the load, L is the span, E is the material part of it. That's the modulus of elasticity. So that's the material part of things. What we're going to learn to calculate is I. That's the value that we're going to calculate in this class. Now, we're not going to calculate deflections, but I want to provide some context here that we are calculating real values. These values can be used in practice. We were talking about the PEs and the FE exam earlier. When you get a PE, you usually make more money because you're stamping drawings and you're approving things and you're responsible for things. I is a number you can take to the bank. Literally, if you can calculate the excuse me, if you can calculate the deflection for a structure and say, yes, it's good, it's not going to deflect too much, you can take that to the bank, and calculating I is a valuable number and something that you can take to the bank. So in practice, you'll see a lot of buildings and structures are made from cross sections that have this I shape here. And the reason we have this I shape is because it reduces deflection using the same amount of material. Here's our neutral axis. Well, what do? We put a lot of area really far away from the neutral axis down here and down here, as compared to taking the same amount of steel and making a rectangle out of it. We're going to get a smaller deflection. So it costs exactly the same. Actually, you can reduce the cost because you need less steel area, and that means less material cost in order to get the same deflection. So we take this area and we put it far away from the neutral axis. Same with wood structures as well. Floor joist, 20 years ago, most floor joists in buildings were made out of rectangular shaped members. Well, now most floor joists are made out of these I-shaped members because it increases the moment of inertia. Okay, so for that first learning objective, it's all about the bending stiffness, right? That's what I is really. It's a geometric part of bending stiffness. Okay, so let's talk now about, let's write some stuff down, moments and products of inertia. And so this is, like we talked about, it's the second moment of area. And it's the geometric bending stiffness. We have actually already studied the first moment of area. So we're doing the second moment of area. The first moment of area was when we did like X bar. and x bar was equal to the integral of x tilde dA divided by the integral of dA, for example. Well, this part up here, not the whole thing, but this is the first moment of area. Or second moment of area. Or area moments of inertia. Same thing, right? Just different names for the same thing here. Is Ix is equal to the integral of y tilde squared times dA. Iy is equal to the integral of x tilde squared times dA, and Ixy is equal to x tilde times y tilde times dA. So the second moment of area just means that it's the moment arm squared, or the distance to the centroid of the differential element squared. And the reason that Ix has a y tilde, Iy has an x tilde, is because Ix represents the moment of inertia relative to the x-axis. Well, what distance describes how far an area gets away from the x-axis? It's the y distance, and we'll talk more about that when we draw some pictures. Now, when we did our centroids by integration in the first moment of area, dA we could pick. Either we could use a dx or a dy. Now, for these, though, we have to use a dy for this one. Yep, yeah, we have to use a dy for that one. And then I had to imagine what the picture looked like for a second. Have to use a dx for this one. And then this can be either a dx or a dy. And we'll talk more about why when we draw some pictures here. We'll talk more about the reasons why when we draw some pictures. So here's our key equations. If we have these equations, if we can figure out y tilde, which we've already done this before, we did this for centroids of areas. You just have to draw that picture and figure out what is y tilde. You have to figure out what is dA. You have to figure out what is x tilde. And then we can solve all this stuff. We can, and these are numbers, remember, these are numbers that we can take to the bank. So let's jump into an example problem here. Let's take an area, and just like we did with centroids for areas a long time ago, it was like topic number 10 or 11 or something like that. We started out with integration, and then we went into composites, and we're going to do the same thing here. We're going to start with integration. On Wednesday, we'll go into composites, which is like rectangles and things that are composed of like the I-beam would be a composite. And so, but we're going to start out with functions here. And if we have a area that we are trying to find the moments and products of inertia for this area right here, and this is a y is equal to x cubed over 4. And we would like to find, oh, I guess we need to know what it's bounded by, don't we? Let me draw the bounds on this here. This is going to be 4 meters from there to there. And so we want to find, for this problem, Ix, Iy, and Ixy. I keep looking back at the chat and I see this, this comment about review sessions. I think it was just a direct message to me. I think, I like review sessions. I think you have to be careful with the review sessions because not everybody can make it to the review session. It can be a little bit unfair. So I would prefer to have, just one review during lecture where, we do the practice exam. That's our review session. And then, but I'm happy to one-on-one individually with you during office hours, do a little mini review session, right? Where, but you have to kind of ask me questions. Otherwise if I come up with things, then it's well, I have to share this with everybody for it to be consistent. So I'm happy to do look at your study guide or answer specific questions that you have, or it's totally fine. I have students that come in office hours and it's just I'm really not understanding this concept. Could we maybe go over a problem? And usually what I do is I just grab a homework problem and one of the homework problems, and we kind of work over and go through those steps, because that can be really effective when you're one-on-one and we're just talking to each other, right, rather than talking during a lecture. So so yeah, if you want to do more one-on-one review sessions, I am all about that. Okay. All right, so here's our example. Let's if we plug in, we can figure out this distance right here. Actually, wouldn't that be 4 cubed over 4, which actually gets us to 4 meters also. So let's just throw that in there right now that we know the height of that thing as well there. So for our solution, let's start by let's find Ix. And we know Ix is the integral y tilde squared dA. And remember that we have to use a dy differential element. So let's draw just like when we did centroids of areas, drawing our representative differential element is going to be a key first step here. So there's our area. I'm just going to draw it again. We know this is y is equal to x cubed over 4. Now, the reason that this has to be a dy differential element is because we need it to be that differential element. As it gets smaller and smaller, it needs to, the center line of that has to be the same distance from the x-axis. And so the center line is the same distance from the x-axis. And so that's why we have to use this dy differential. Let me do a different color here. So our center line, that is the same distance from the x-axis, and our dy, though, is the height of that thing. Now, just like we did before, the key point is where our differential element intersects with our function right there. That's where we know the relationship between x and y. So for example, we know this distance here is equal to x. And then if we know that distance, then we know this distance right there is equal to y. So now that we have this drawn, we can start to figure out well, what is y tilde. And what is dA? Well, let's start with dA. dA is just the area of that differential element. So it has a height of dy, but what is the width? Oh, is it 16 meters? 4 cubed? Oh. Oh, shoot, I just realized that should not be 4 meters. I don't know why I don't know where I even saw 4 meters. Can we change it? It'll just, so I follow my notes here. That should not be 4 meters. That should be 2 meters. I don't know where I got 4 meters from. There's like not 4 meters written anywhere on my paper. Oh, maybe it was the 1/4 up here. And then, so that's going to be 2 meters. And then this is going to be 2 cubed over 4, which now that should be, what is that? Two cubed is 8 divided by 4. So that is 2 meters. Okay, so yeah, let's change that so it fits in with the numbers that I've calculated here. So sorry about that. Okay, so we're going from 0 to 2 meters, and then that makes the bounds on the y-axis also from 0 to 2 meters. Okay, and then I asked that question of what is the width of my purple rectangle that we have up there, and I see an answer, the correct answer in there. It's actually not 4 minus x anymore, but wouldn't it be 2 minus x, because we are saying that this point right here is 2 meters, and so the width of that rectangle right there is going to be 2 minus x. But yeah, before column, it would have been 4 minus x before I changed the original given information. So that's exactly the same thing that we did before. It's just finding the area of our rectangle. And so drawing this picture is super helpful, right? So dy is, or dA is dy times 2 minus x. Now we do need to substitute out the x there. And so if we solve for this, we know that x is going to be equal to 4y to the 1/3. So since we're doing a dy differential element, we do need to substitute out that x. Now, how about our y tilde? Remember, the tildes denote the centroid of our rectangle. So our centroid is going to be right there. So that is going to be our x tilde, and y tilde is the centroid of that. Y tilde is just equal to y. So it's that same distance, right? Up from the x-axis to y. So y tilde is just equal to y. Well, now we can find Ix is going to be the integral from 0 to 2 meters times a y tilde squared times dA. And so we're going to end up with the integral from 0 to 2. Y tilde is just y, so y squared. dA is 2 minus 4y to the 1/3 times dy. So now we've got everything in terms of y. We can plug this into a calculator. We can do this by hand. We are going to find that Ix is equal to, when we plug this in here, 0.533. And any ideas? What are the units on this moment of inertia, the second moment of area? Let's think about what we're doing here. If we think about what are the units on y tilde? If it's a distance, right? The units on y tilde are, this is meters squared, isn't it? What's the units on an area? It's also meters squared. So our units, moment of inertia, second moment of area, it literally is just the area times the moment arm squared. So we end up with meters to the 4th. And then, yes, regarding the question in the chat there, just to check, the X and Y tilde are just the centers of the rectangle we are looking at. That is true. It is X tilde and Y tilde. Is just where is the center of that rectangle and relative to the rest of the things that we know, right? Symbolically relative to X and Y and the equation that we're given. X tilde and Y tilde are always the centroid of the individual rectangles. That's all there is. That's all there is to it. That is really about drawing that picture and then plugging it into our equation. Let's move on to IY. IY we know is the integral x tilde squared times dA. And again, because we want the center line to be all the same distance, we now have to use a dx here, and that should be an x tilde squared. X tilde squared times dA. And so we have to use that dx differential element there. So let's draw another picture here. We got x and y. We've got our function here. We're going to draw a dx differential element. And I like to draw my differential elements relatively big, just so it's easier to look at the dimensions on these things. So there's our width of that differential element is dx. Wouldn't the height of that differential element be equal to just y? Because we know right there where we cross the function, that's our x and y. It's where we know the relationship, because we have this function x cubed over 4. So we know if we know x, we can find y. So that means our dA is equal to y times dx. And then we need to find x tilde. Well, x tilde is the centroid of that rectangle. I always like to draw the location of that centroid. I just did it there in red. And so x tilde would be that distance right there. X tilde is just equal to x. And so now we can plug this in. Ix is going to be the integral from 0 to 2 meters now. X tilde is x squared, and then times a y dx. Oh, we need to substitute out y. What is y equal to? It's x cubed over 4. So x cubed over 4 times dx there. Oops, and why did I call this Ix right here? That should not be Ix. Let's fix that. It's right there, that is incorrect. I'm doing Y, right? So I'm just gonna erase it and I'll highlight it. So IY, that's what we're working on right now, right? Is IY. So this is IY. And before I give us the value, or before you plug it into your calculator and come up with a value, based on the concept of what the moment of inertia represents, where area further from the neutral axis provides a larger bending stiffness, right? So I can't bend the yardstick this way, but I can bend the yardstick this way, right? I can go boom like that. I can't bend it that way, but I can bend it this way because I have more area, right? When I'm doing this way, I've got more area from the neutral axis. Well, in this problem, it's whichever one has more area from the X or the Y axis. So if I was bending about the X axis, and think about this as like my yardstick, instead of having a rectangular cross section like this, think about it as having the cross section of that function, that kind of ramping and curving function there. Now, let's say this is the X axis. right here. If this is the x-axis, when I try to bend about that axis, that's the one that I can't get the board to bend on. When I try to bend about this axis, let's call that the y-axis. When I try to bend about that axis, I can, right? I can bend it. I can bend on that axis, but I can't get it to like bend on that axis right there. So my x-axis bending is really strong for this yardstick. My y-axis bending is not, because the area is not very far away from the y-axis. Now let's think about our cross section here. The bigger I means less bending. Like the bigger I on the yardstick, that's the one that has less bending. That's the one I can't cause it to bend. By looking, if my picture is relative to scale here, would I expect IY to be bigger or smaller than IX? We found IX is 0.533. So relative to bending about the x-axis, can I tell like which one has more area further away from, do I have more area further from the x-axis, or do I have more area further away from the y-axis? Anyone, what do you think in the chat? Is IY going to be, do I have more area, like if I'm thinking about bending about the y-axis versus bending about the x-axis, which one is going to be bigger? So if I was bending and trying to bend the yardstick about the y, well, don't I have quite a bit of area, like relative to the y-axis? Kind of got all this area that's pretty far away. Relative to the x-axis, I really only have like a little bit of area that's that far away from the x-axis. So IY is actually, we're going to get a bigger number. And so IY, when we plug it in, we're going to get 2.67. So it's almost, it's more than 5 times bigger. And it's meters to the fourth. Again, we see that's those same units there. So just to relate that back to where we started today's discussion about it being the geometric part of bending stiffness. So just like those eye shapes, right? When we did those eye shapes here, when I showed you those pictures of those eye shapes, you get all this area down here and down here that's really far away from that axis. That's really a large moment of inertia, and larger moments of inertia means it's stiffer. You're going to get less deflection, less bending. And by bending, I mean like the actual bending deflection that's occurring, like when I show you the yardstick bending. Okay, let's, we need to go into our IXY. So IXY is the integral of x tilde y tilde times dA. And with this one, remember, it can be either dx or dy. It doesn't matter for this one. Let's just go ahead and use dx, just because it was the last thing that we drew. It's right here. So here's our dx differential element. So we already know that x tilde is equal to x. We already know that dA is equal to y times dx. Now, the only thing that we need to find is y tilde. And y tilde is equal to just half of y. It's just equal to y over 2. If we plug in our function here, isn't it x cubed over 4? That whole thing divided by 2. So we can find IXY would be the integral from 0 to 2. X tilde is x. Y tilde is x cubed over 4 divided by 2. And then dA is x cubed over 4 times dx. So we can label the different parts of this thing, right? That is x tilde. This whole thing right here is y tilde. And then this is dA. when we plug in our numbers here, we're going to find that IXY is equal to 1.0 meters to the fourth. So still the same units. That number, though, is not something we could use to calculate a deflection. It doesn't tell us how much bending I can do in this yards. It doesn't tell me how much I can do this or how much I can't do this in the yardstick. It has a mathematical meaning, though. And let's start by looking at the possible range of values on IX and IY and IXY. Because if you look at your equation, like up here in the left, top left corner, x tilde squared times dA. Well, dA is always going to be positive unless we had a black hole, and we're not going to do any black holes in statics. So our area is always going to be positive. Even if we're in a negative quadrant, because x tilde is squared, that will always be positive as well. So IX and IY will always be positive. IXY, though, if you look at this equation, if x tilde is negative or if y tilde is negative, then IXY is going to be negative. So while IX and IY are always positive, IXY can be negative, it can be positive, or it can be zero. When IXY is zero, it means that IX and IY are principal moments of inertia. Principal means max and min. It doesn't tell us which one. We have to look at the relative values and figure out which one's the biggest and which one's the smallest. So for our example, IX and IY are not principal because IXY is not equal to zero. Are not principal because IXY is equal to 1.0. So when we start up on Wednesday again, we will talk about when is IXY equal to zero. For now, though, just know that really we just need to know that if IXY is equal to zero, IX and IY are principal, meaning maximum minimum moments of inertia. So our IX and IY are not. In order to get to the maximum and minimum, we need to rotate our axes. That's how we could get to maximum minimum, which we will talk more about as we get into it. I'm not going to talk about it much on Wednesday, but we will talk about it more on Friday. So sorry I went over. You all have a